Hello everyone, welcome back to the training. Hi guys, can you hear me clearly?
Yes, Chirag, you're audible.
Perfect. Just a second and we'll start. All right, so let's get started. Welcome back to PyNet Labs. As you all know, my name is Chirag, and in this webinar today, we'll be talking about the significance of metric manipulation. So in metric manipulation, we can say it can help us in various scenarios, but doing it without understanding the impacts of it can also lead to various kind of troubles. So in this webinar today, we'll be talking about all the things related to metric manipulation. First of all, let's understand what metric manipulation is all about. So when we talk about metric manipulation, it refers to the process of modifying routing metrics. So we can say metric manipulation is simply modifying routing metrics. So metric manipulation can be a powerful tool in order to administer network or optimize network according to your requirements. However, as I mentioned earlier, without understanding it and doing it without understanding the impact of how it will bring out the outcome can lead to suboptimal routing decisions, can create loops in your network, can create unnecessary issues in your network. So metric manipulation has to be understood first, and then only we can manipulate it by understanding what exactly will be the impact of that change, right? So in today's webinar, we will first discuss the different types of metrics which are used by different types of routing protocols. Then we will talk about how we can manipulate them and what changes will occur and like what impacts it will make. So first of all, let's try to understand the metric of different routing protocols. Now, routing protocols use different kinds of metrics to determine the best path, right? If, for example, I have a router R1 connected to R2, connected to R3, and then connected to R4. So in order to reach R4 from R1, I have two possible ways. Either I can go via this link or I can go via this link, right? But which one is the better one? That depends upon what? That depends upon the metric. Let's assume that RIP is something which we have configured, routing information protocol. Now, if you know, routing information protocol, RIP uses the metric of hop count, right? So in that case, the hops will be considered to find out the best way. So if I go via the first way, we have two hops. If I go via second way, then also we have 1 and 2 hops. That means both the path have same metric, which will lead to equal cost load balancing. That's going to happen only in the case of RIP. But if I replace RIP with OSPF, so OSPF is going to consider the bandwidth of the link in order to calculate the metric. And in that case, if for example, let's say this is a 1 Gbps link, this is a 1 Gbps link, this is a 10 Mbps link, and this is also a 10 Mbps link. Then in that case, OSPF will simply consider this one as the best path because of having a better bandwidth on that way. And there will not be equal cost load balancing, rather the data will be sent via router 2. So that's basically the role of metric, which we observe in various kinds of routing protocols. Now, metric depends upon various factors. Like for example, if I talk about the metric of EIGRP, the default metric of EIGRP, it depends upon bandwidth and delay. When we talk about bandwidth, it is the amount of data which you can send over a particular link for a given period of time. Then when I talk about delay, delay is the amount of time which that data will take to travel from one point to the other. So we can say this is the amount of data this is the amount of time. Then if I talk about OSPF, the OSPF metric is cost. Cost is simply, we can say, this can be calculated by considering a reference bandwidth and then dividing that reference bandwidth with the link bandwidth. We'll talk about this later on in detail. Then if we talk about RIP, it uses hop count. Hop count is simply the number of hops that you must pass to reach your destination. Then in EIGRP, some other factors like load, MTU, all these get into picture, which play an important role, but by default, their value is not considered. So when I talk about EIGRP, let's first start from that only. When I talk about EIGRP, we can say is dependent upon two types of values. The metric of EIGRP can be calculated on the basis of variables and on the basis of constants. So when I talk about the variable values, we get to see bandwidth, we get to see delay, we get to see load, reliability, and MTU. So let's begin from EIGRP metric calculation. Now, EIGRP metric includes bandwidth, delay, load, reliability, and then MTU. Bandwidth, as I mentioned, is the amount of data which you can send on a link for a given period of time. Now, when you will consider this while calculation, you will consider the slowest link. For example, you have R1 connected to R2, connected to R3. Let's assume the link bandwidth between R1 and R2 is 10 Mbps and between R2 and R3 is 100. So while calculating the metric from R1 to R3, I will consider the slowest bandwidth, which means I'll consider 10 Mbps, not 100 Mbps. Then when I talk about delay, delay is the amount of time it takes to move from one point to the destination, right? So the total delay will be considered while calculation, which means that whatever delay will be there for this interface, and then further if let's say this is the interface. So for all the three interfaces, I'll take up the delay, I'll add them together and will consider that. This simply means that bandwidth will be considered as the slowest one. Delay will be considered as the sum of delays. So sum of delays will be considered while calculating the metric for EIGRP. Then load. Load is the current load on a slowest link from a source to destination. This can be expressed in percentage. And if for example, a link is completely loaded, that means it is fully utilized. Then when we talk about the next factor, which is reliability, we can say this is the reliability of a path to a particular destination, like how reliable that path is. This can be can range between 0 to 255. The maximum transmission unit is basically the MTU size of packet which you can send over a particular given link. So these are the 5 variables which can impact or which can make changes in your EIGRP metric. Now, along with these 5 factors, the metric calculation also depend upon some K values. We have got some 5 K values as well along with that, which are K1, K2, K3, K4, and K5. These are going to be some constants. Now, K1 by default is set to 1. K2 is set to 0. K3 is set to 1. K4 is set to 0. K5 is set to 0. Which means that by default, when I do the calculation of EIGRP metric, EIGRP will be considering the constant values of K1 and K3 only, that is 1. For the remaining K2, K4, and K5, we'll be using zeros. Now let's try to understand what is the formula of calculating EIGRP metric. I'll take it to the next page. Metric calculation of EIGRP can be done by using a formula, which is K1 multiplied by bandwidth plus K2 multiplied by bandwidth divided by 256 minus load plus K3 multiplied by delay, and then this whole thing is further multiplied by K5 divided by reliability plus K4, and then again it is multiplied by 256. Now, if we replace the values of K1, K2, K3, K4, K5 with zeros and 1, what we will get as the outcome is K1 will be 1, right? 1 multiplied by bandwidth is bandwidth. Plus K2 is going to be 0. So 0 multiplied by anything divided by anything becomes 0. Plus K3 is again 1. If you remember, I have mentioned here, K3 is 1, right? So K3 multiplied by delay will also give me just delay. And this complete section is also going to come as 0. But if it comes as 0, that means the whole thing becomes 0, right? So we consider it as 1. When your K5 is 0 and reliability is being divided, you will consider it as 1. So that becomes 1 multiplied by 256. So what we got at the end is 256 multiplied by bandwidth plus delay. So by default, that's why we say by default, the metric calculation of EIGRP depends upon bandwidth and delay, where bandwidth is going to be the slowest bandwidth of your link and delay is going to be the sum of all the exit interface delays. If you have got any questions in this part of EIGRP metric calculation, then please let me know in the chat box. Otherwise, we'll jump on to OSPF metric calculation and we'll understand that. Okay, if it is clear, just give me a thumbs up. Perfect. All right, great. Okay, now let's talk about the next protocol, which is OSPF. Let's see how OSPF calculates metric. When I talk about the OSPF metric is called OSPF cost. And this cost can be simply calculated by dividing reference bandwidth with the link bandwidth. reference bandwidth by default is going to be considered as 100 Mbps. So 100 Mbps divided by the link bandwidth. So for example, let's say I have R1 connected to R2. And this link we have is of fast Ethernet, let's say. So which basically means the bandwidth here we have got is 100 Mbps. So what will be the cost, guys? Cost is going to be simply 100 divided by 100, which means 1. If, for example, the link was of Ethernet with a bandwidth of 10 Mbps, then I would have divided 100 by 10. And my cost would have come as 10, right? But what if this link was of 1 Gbps, let's say this was 1000 Mbps. So in that case, we will be dividing 100 by 1000. And when we do such division, the outcome is going to be 0.1. And since it is cost, it cannot be in decimal. I'll convert it to the nearest integer. That means 1. So what happened right now? Let's try to understand. For Ethernet, when I divided 100 by 10, I got the cost as 10. For fast Ethernet, where I divided 100 by 100, I got the cost as 1. For gig Ethernet, when I divided 100 by 1000, again I got 1. If let's say this was 10 gig, then also the calculation would bring out 0.01 and we will round it off to 1. That means 10 gig also will be giving you the cost of 1. So it becomes a little difficult to identify and to differentiate between a fast Ethernet link, a gigabit Ethernet link, and a 10 gigabit Ethernet link when the devices are connected with OSPF, because all of them will have the same cost, right? Why is that happening? Because of the reference bandwidth being 100 Mbps. So if it was something higher, if it was something like, let's say 1 Gbps, then it would have been a little easy to understand the difference between fast Ethernet and gigabit Ethernet. Because now fast Ethernet's cost will come out as 10. Gigabit Ethernet will come out as 1, right? So we can change this reference bandwidth, but again, that is a metric manipulation case. In that scenario, you again have to understand the impacts, because this can lead to various kinds of issues as well. So you need to know how you can change the reference bandwidth in order to make sure that everything goes well. And along with that, you are able to differentiate between both the different kinds of links, right? So this is something which we will be exploring later on. I have kept some situations ready. I have kept some labs ready where we have OSPF configured. So we'll try to change the reference bandwidth there, and we'll see how the metric gets different after we change it from 100 Mbps to something higher. We'll talk about that later on. As of now, if there is any question regarding the calculation or the cost process of OSPF, then please let me know in the chat box. Otherwise, give me a thumbs up if we are good to move ahead. Perfect. Now it's time to understand the big protocol, BGP. So let's talk about that also. Now BGP selects the best path on the basis of various values. See, we all know BGP is not a protocol which we use internally, right? We use it for external communication over the internet. So the task with BGP is not to make data reach the destination quickest. The task is to make communication between different autonomous systems. So in that BGP case, we don't refer to bandwidth and all very much, but we refer to various kinds of factors. So we'll be discussing about these factors, and we will also do a basic lab where we'll try to see how BGP metric can be manipulated. So let's first understand what are the rules on the basis of which the best path is determined in the case of BGP. So the very first criteria on the basis of which BGP finds the best path is weight. So it will prefer the path with highest, we can say, weight. That's the first basis of finding out which is the better path. If let's say weight comes out to be same, then next it will look into local preference. So it will prefer the path with highest local preference. Now, a good thing to know is that local preference by default for all the paths is going to be 100. You can change that value in order to make metric manipulations. Then if let's say the local preference also is same, then we will prefer the path learned via network or aggregate command. So if you know how BGP is configured, so in that we can use the network or aggregate command to add in the networks. So in that scenario, the path will be preferred first, and after that I will consider the redistributed paths. So that is the case there. After that, if let's say these values also come out to be same, then we refer to the AS path, like how far the destination is or how far the particular network is situated. In order to understand the concepts, we can say, let's say this is AS 100, this is AS 200, this is AS 300. So when my router will learn about any network of AS 100, it will add in the information that it is coming from this path. So from 300, we have to go to 200, then we have to go to 100. So whatever path will be there with the shortest path, like whatever link or whatever route will be there with the shortest AS path, that will be preferred next. So it prefers the path with shortest AS path. Then the next will be prefer the path with lowest origin type. So what is the origin type of the path? That also is something which can be understood to find out the best path calculations. Either it can be IGP, it can be EGP, or it can be incomplete. So you must have observed while checking the BGP database table that there is usually something like this written, I, E, or a question mark next to your particular path. So in this scenario, I is, we can say, the most preferred, which is IGP, EGP is next preferred, and then question mark, which refers to redistributed path, unknown path. These are preferred last. So if there is a path which is learned via I and is learned via redistribution, so obviously we'll be referring to this one. We'll be considering that one as the better path. After that, the sixth way, or we can say the sixth factor which calculates the best path, is multi-exit discriminator value. So it will prefer the path with the lowest MED, which is multi-exit discriminator. After that, we can say seventh factor is preferring it will prefer eBGP over iBGP. Then we can say it will prefer path with lowest IGP network metric to the BGP next hop. So lowest IGP metric will be considered. After that, we can say it determine if multiple paths are required to be installed. So at this point, it will consider if, for example, more than one path should be installed into the routing table or not. If let's say no, then we will continue ahead with the rest of the factors to find out the best path. And then we'll get to the 10th point where we can say the oldest path will be considered. So whatever path is installed at the first place, that will be considered as the best path. So the oldest path is considered. And then we can say the last, not the last, the next one is preferring the path, prefer the path that comes from BGP router with lowest router ID. After this, we can say if, for example, router ID or the originator ID is same, then multiple paths will be clustered together and will be considered. So these are some criteria on the basis of which BGP tries to find out whichever is the possible best way of reaching the destination. We'll also be trying to observe this using a lab and practical, and we'll also observe how it works in the case of OSPF and EIGRP and how we can manipulate things there. So let's get started with the lab part and let's try to understand how things get different when we manipulate the metric a little bit and how it can benefit us, how it can lead us to various kinds of problems and what all possibilities are there. So I'll share my other screen. And I hope my second screen is visible now.
Yes.
Great, perfect. So the very first thing which we will understand today is the static floating routes. So I have kept this lab ready here with me. This is a topology where we have got 4 routers, R1, R2, R3, R4. Now R1 is aware of all the networks. We have installed the routes for all the networks. Similarly on R2, R3 and R4. And these are already configured with the IP addresses. DHCP pools are also created. PCs are also assigned with the IP address. But the thing is, when I go to R1 and I try to look into my routing table, when I say enable show IP route, I can see that there is a static route for 210.2.0, but there are 2 possible ways of reaching it, 12.10.1.2 and 13.10.1.2. And both are installed in the routing table, which means that both are being used for reaching the destination. This is an example of equal cost load balancing. But when I look at the scenario, I can see that this way, when I go via R2, I have the bandwidth of 100 Mbps. But when I go via R3, the bandwidth is just going to be 10 Mbps. Why? Because this is an Ethernet link, right? And here we have got fast Ethernet link. So according to me, the better way of reaching destination is sending the complete data via R2, right? Instead of equally balancing the data over both the links, my primary route should be via R2, and then I can say my secondary route can be via R3. I don't want R3 to be used always. I just want it to get into picture when my route via R2 is not available. So how to do that? We can do that by manipulating the AD values a little bit. So I'll go to my R1. First of all, I'll remove the routes for 210.2.0. I'll say config T, no IP route, 210.2.0, 255, 255, 2550, 12.10.1.2. And then I'll also remove it with the next hop, 13.10.1.2. Let's re-verify the routing table, do show IP route. Okay, now I don't have any static route for 210.2.0. Now it's time to add it again, but with the manipulations. So I'll say IP route 200.10.2.0, 255, 255, 2550. Next hop 12.10.1.2. This is the primary one, right? After this, if I put a question mark, it asks me about the distance metric for this route. Now, by default, it is set as 1. But if I want to manipulate that, I can do that. What I'll do is I'll set it to 5, for example. Then I will add the next possible way. IP route 210.2.0, 255.255.255.0 via the next hop 13.10.1.2. But this time I'll set the distance metric as 10. And now if I check my routing table, show IP route. So I do have a path for reaching 210.2.0, but now it's not going to equally load balance the data over both links. It will just refer to the path via 12.10.1.2. Why? Because we have manipulated the metric a little bit. Now the metric there is 5, right? And the other path, the 13.10.1.2 path, will only get installed if this one is not available, because that is having a metric of 10. Now if I say ping 210.2.2, which is a device of that network. Okay, let me re-verify the IP addresses. Okay, I got the reply lastly. So let's ping it again. There. So we are having a reachability. But what about the path? Which way is it going? Let's try that. Let's try to find out that. Trace route 200.10.2.2. And I can see it is going via 12.10.1.2, which is the 100 Mbps link, not via 13.10.1.2. Because only the best and primary path is getting installed into my routing table. Why? Because I manipulated the metric. Now, if in case my FA01 goes down, let's assume that because of some issue, the interface FA01 goes down. What to do in that case? Now, if I check my routing table, show IP route, still I can reach 210.2.0, but this time via 13.10.1.2. Why it got changed? It got changed because my primary path is no longer available. That's why the path having the metric, or we can say the AD of 10, is getting installed into my routing table now. That's how you create static floating routes. Now, still, if I try to ping 210.2.2, I'll have the reachability, but this time my data will go via router 3. We are getting the replies, right? So this is the way how you can make sure that the primary and secondary path gets installed into your routing table only when it is required. Make sense, guys? Any questions in this? Same way, we can add the routes on router 4 as well. If I go and check the CLI of router 4, show IP route, if I check the routing table, here also I can see 210.1.0 is getting equally load balanced on both the links. So what I'll do is I'll make the first link as the primary and the second one as the secondary. So let's first remove it. Config T, no IP route 210.1.0, 255.255.255.0, 24.10.11, then 34.10.11. After that, we will add the route, IP route 210.1.0, 255.255.255.0, 24.10.11 with an AD of 5, and then IP route 210.1.0, 255.255.255.0, 34.10.11 with an AD of 10. Show IP route, and we will only observe the one with 24.10.11 as the next route. That's how you can configure the static route. That was an example of how static floating routes are configured. Now let's jump to EIGRP. Now in the case of EIGRP, we have understood there is a complete formula of how the metric is calculated, and that by default depends upon bandwidth as well as the delay, right? So we'll try to calculate this metric now. If I go to R1 and I try
sorry to disturb, Chirag. This is Shuman. I want to know that the backup route information where router is kept.
Sorry, what's one?
The backup information. The floating router have two static route we configured. One is appearing in that routing table, but the second one where router is kept. How the second one is if the primary goes down. So can you tell me where it is kept by router? Why
so it depends. Yeah, it depends upon the routing protocol which we are using. If, for example, I talk about EIGRP, then the second best route is stored in the topology table. If I talk about OSPF, then there is a database table maintained in which the information about all the routes are stored. Similarly, in BGP also, a database table is maintained, and that's how it works.
For static?
Static doesn't maintain any tables. It will store the information in the router's memory. So you need to understand the control plane, data plane for that. Routing information base is created in which the best routes are installed. Otherwise, they are kept in some kind of memory, which will be referred to later on. When in scenario where there is no best way, then only the router will refer to that particular information.
Okay.
Yeah. Now, in the case of EIGRP here, I have already again configured EIGRP between these routers. And if I go to my router 1 and try to check my routing table, show IP route, I can see there is a EIGRP route for 192.168.2.0. In this EIGRP route, we can see that the AD is 90 and the metric is 30,720. This must have been calculated with the help of those values, bandwidth and delay and so on. And we'll try to do the same here. So when I talk about bandwidth in this case, we can see the link is fast Ethernet link. So it's going to be 100 Mbps, right? After that, when I talk about delay, so delay is considered as the exit interface delays. So we have got two exit interfaces here. One is FA01 of R1 when it takes exit from R1. Then in order to reach this network, it has to take the exit from FA01 of R2 as well. So we will be considering the delay of FA01 here and the delay of FA01 R2 of R2 basically. So if you remember, the metric calculation gave us the formula 256 multiplied by bandwidth plus delay, right? This was the formula. So let's use the same and let's try to calculate the bandwidth here. Sorry, let's try to calculate the metric here. I'll go to show interface FA0/1. And when I check that information, I can see the delay is 100 microseconds. Now you have to convert it into tens of microseconds, for which you will be dividing it by 10. So 100 will be divided by 10, which will give us 10, right? Similarly, on R2, if I check show interface FA01, I can see the delay here is 100. So we consider the delay in the tens of microseconds. So again, you will have to divide it by 10. This means that metric should be equals to 256 multiplied by bandwidth is going to be 100 plus delay 100 divided by 10 plus 100 divided by 10, which simply means that metric is equals to 256 multiplied by 100 plus 10 plus 10, correct? Which means metric is equals to 256 multiplied by 100 plus 20, that means 120. So 250 into 120 should be my metric. I'll open my calculator here on the screen and we'll try to do this calculation. 256 multiplied by 120. And there you go, we got the outcome 30,720. If I go to R1, if I check the information, show IP route, then I can see the metric is 30,720. If, for example, I try to manipulate some value, if, for example, I try to set a different delay on a particular interface and try to observe how things get different there, then what will happen? Let's see. Let's say, for example, I configure the delay of 200 here on FA01 of R1. Then the calculation would have been a little different, right? This would have been 200 divided by 10. This would have been 100 plus 20 plus 10. And this would have been 256 multiplied by 130. And as the outcome, I should be getting, let's see, 256 multiplied by 130. I should be getting 33,280. So let's see if we get that value or not by changing the delay. I'll go to R1, I'll go to FA01, config T, interface FA01, and there I'll say I want to set a delay of, see, when I put a question mark, it says that it is going to set the delay in tens of microseconds. So if I set 2, that means it is going to consider it as 20. So if I set 20, it will be considered as 200. Okay, we can see the EIGRP neighborship is down and then it comes up again. If I check the information of FA01, I can see the delay got updated to 200. Let's check the routing table now, show IP route. Okay, it is showing me a delay of 33,280. If I go back to my calculator and try to do the calculation again, 256 multiplied by 130. So we are getting the same value there. And we can see the metric is now updated to 33,280. So changing these values will impact your metric. And on the basis of all the available paths, let's say you have got 2 more paths to reach R2. You can change the value according to your choice and you can select the best way of reaching your destination depending upon how you want the routers to act. Now moving on to OSPF example. In OSPF, we discussed one problem, right? We discussed how the metric or the cost for fast Ethernet link and gigabit Ethernet link comes out to be same. Now in this scenario, I have taken 4 routers, R1, R2, R3, R4. These 4 routers are configured with OSPF. They are basically having their router IDs as 1111, 2222, 3333, and 4444 respectively. Now, when I go to R1 and I check my routing table there, if I say, okay, let me skip the time a little bit. If I say enable show IP route, I can see I can reach 172.16.2.0. Okay, I was checking this and I think I should reload the device. All right. Just a second, guys. I think I was testing something. What a cost. Okay, I'm setting the reference bandwidth back to the default one, which is 100. I was testing something at that time. I changed it and it is still the same. So let me update that quickly. Auto cost, reference bandwidth 100. And then on router 4, we'll go to the CLI and say enable config T router OSPF 10 auto cost reference bandwidth 100. Okay. Now, if I go to R1, right now they are behaving by default, like how they should be behaving without making any changes in them. If I go and check my routing table here on R1 by saying show IP route, then I can see that 172.16.2.0 is reachable via 10.13.1.2, and it should also be having the route clear IP OSPF process. Okay, I think there is something messing up with my packet tracer. What I'll do is I'll quickly create a similar kind of scenario here. I'll take 4 routers. Let's connect them together. So this is a fast Ethernet link. I'll go to my router 0 and I will add some gigabit Ethernet links. I think I need to take some other routers. No worries. Let's go to routers. Let's take. Okay, we'll go to router 1 and we'll shut down the router. That's how you can add your ports. So I'll add 1 fast Ethernet port and 1 gigabit Ethernet port. Similarly, I'll go to router 5. I'll shut it down, add 2 fast Ethernet ports like this, turn it on again. I'll turn on the router 1 again. I'll go to router 6, shut down. I will add 2 gigabit Ethernet links here. Then lastly on router 4, I'll shut it down and we'll add 1 fast Ethernet link and 1 gigabit Ethernet. Turn it on again. Now it's time to connect the cables. So let's connect. This is a fast Ethernet to fast Ethernet connection, then fast Ethernet to fast Ethernet again, then gig Ethernet to gig Ethernet, and then gig to gig. Now I'll be configuring them under OSPF 10 area 0. Along with that, what I'll do is I'll create a loopback 0 on router 1 with the IP 192.168.1.0, 1.1/24. Similarly, a loopback 0 on router 4 with the IP 192.168.2.1/24. And we will observe how they reach to the destination from one router to the other. Let's begin the configuration on router 1. I'll go to the router 1 CLI, say no to the question, enable config T, host name R1, interface FA00. Let's assign it the IP address 10.12.1.1, 255.255.255.252. No shutdown. Exit. Then interface gig 1/0. And there I'll put the IP address as 10.14.1.1, 255.255.252. No shutdown. Exit. So this is my 10.12.1.0/30 network. This is my 10.14.1.0/30 network. Here I'll use 10.23.1.0/30. And here I'll use 10.43.1.0/30. Let's go and let's configure the other routers. CLI. Say no to the question. Enable config T host name R2. Interface FA00 will get the IP address as 10.12.1.2, 255.255.255.252, no shutdown. Then interface FA1/0 will get the IP 10.23.11/30 subnet, and then no shutdown. Exit. Then I'll go to router 3. Say no to the question again. Enable config T host name R3. Interface FA00 will get the IP address as 10.23.1.2/30 subnet, no shutdown. Then interface gig 1/0 IP address 10.43.1.1/30 subnet, no shutdown. Interface loopback 0 IP address 192.168.2.1/24 subnet. Exit. Then I'll go to router 4 CLI. Say no to the question. Enable config T host name R4. Interface gig 1/0 IP address 10.43.1.2 255.255.255.252, no shutdown. Exit. And then gig 00 IP address 10.14.1.2/30 subnet, no shutdown. Exit. I think I didn't create any loopback on router 1. Let's verify that. Show IP interface brief, and yeah, so let's create the loopback. Interface loopback 0 IP address 192.168.1.1 255.255.255.0 and exit. Now it's time to configure OSPF between these routers. So let's begin that now. Router OSPF 10, router ID 1111, and interface range FA0/0, gig 1/0, loopback 0, IP OSPF 10 area 0. So I have configured OSPF on all the interfaces and I have assigned the router ID 1111 to router 1. This is my router 2, router OSPF 10, router ID 2.2.2.2, interface range FA00, FA1/0, IP OSPF 10 area 0. Exit. Let's go to router 3. Router OSPF 10, router ID 3333. Here we have got 3 interfaces. So interface range FA00, gig 1/0, loopback 0, IP OSPF 10 area 0. Exit. And then on R4, router OSPF 10, router ID 4444, interface range gig 0/0, gig 1/0, IP OSPF 10 area 0. After that, we'll skip the time so that these routers can quickly become neighbors. Okay, we have got the neighborship with 1111 and then 3333 as well. Now, if I go to R1 and try to check my routing table there, let's see what do we get. So when I check my routing table at R1, 192.168.2.1 is reachable via 10.12.1.2 and is also reachable via 10.14.1.2, which is pretty correct, right? Both the ways can be used for reaching destination. But there is one issue. Here, the cost for reaching via 10.12.1.2 is considered as 3. Then the cost for reaching via 10.14.1.2 is also considered as 3. But when I look at the links via R2 is fast Ethernet links, but the links via R3, which is basically in this scenario router 6, that is via that are gigabit Ethernet links. So according to me, the better path for reaching destination is via router 3, right? Do you agree with me? Give me a thumbs up. Do you think I'm saying correct? Yes, perfect. So in this scenario, my OSPF will not differentiate between both the links because of reference bandwidth being 100. So when it calculates the cost for first way, it will divide 100 by 100 and will get 1. But when it do it for the second way, which is the gigabit Ethernet way, it will divide 100 by 1000. And after rounding it off, it will again become 1, right? So that's the issue there, because of which we are considering both as the same, we can say, both the links having the same cost. That's why we are equally load balancing the data over both the possible ways. So how can we fix that? We can fix that by changing the reference bandwidth. So we'll change it from 100 Mbps to, let's say, for example, 10,000 Mbps. And then after that, differentiating between fast Ethernet and gigabit Ethernet will become easy, because at that time, my fast Ethernet will be divided. I mean, the 10,000 Mbps will be divided by 100, and then 10,000 Mbps will be divided by 1000. So there will be a cost of 100 for fast Ethernet and 10 for gigabit Ethernet. So let's do that. So what you need to do is you simply have to go to router OSPF configuration, and there you will write down the command auto-cost reference bandwidth. And if you put a question mark, you can set the reference bandwidth in megabits per second. So I'll set it to 10,000 megabits. Then it gives you the warning that please ensure reference bandwidth is consistent across all the routers. So you need to make sure that it is same on all the routers. Otherwise, router 2 will calculate it on the basis of 100 Mbps and router 1 on the basis of 10,000 Mbps. So you need to make sure you are keeping it same on all the routers. I'll go to router 2 now. There I'll say router OSPF 10 auto cost reference bandwidth 10,000. Exit. Then router 3, router OSPF 10 auto cost reference bandwidth 10,000. Exit. Then router 4, config T, router OSPF 10 auto cost reference bandwidth 10,000. After this, if I go back to my router 1 and try to check my routing table again, show IP route. So now I can see only one way to reach my destination 192.168.2.1, and that is via 10.14.1.2. But does that mean I have no way of reaching it via R2, which is basically the fast Ethernet link? No, that is incorrect. If in case this way is not available, then obviously the path which is having a higher cost will be considered, and that particular route will get installed. So by changing the reference bandwidth, I can make sure that my routers can differentiate between fast Ethernet links and gigabit Ethernet links and 10 gigabit Ethernet links and so on. Make sense, guys? Any questions in this? All right, so that's how you can make sure that OSPF is differentiating between the routes which are having a different cost. Now the next is BGP. So let's jump on to EVNG now, because yeah, here we'll be able to observe the BGP working a little bit better. So here also I have a similar kind of setup like I have shared in OSPF. I have R1, R2, R3, R4, and R1 is participating in autonomous system 100. R2 in 200, R3 in 300, and R4 in 400. So by default, BGP does not enable equal cost load balancing. Though we will be getting the route to reach R1 on R4 via two ways. Like for example, here if I show you R1, then in R1 I have created one loopback. Show IP interface brief. So here is a loopback one which we are advertising into BGP. So if I go to R4 and check my routing table there, show IP route. So I can see 1.1.1.0 is reachable via 35.10.11, which is basically R2. So by default, as I mentioned, BGP will not use equal cost load balancing. And if I use the command show IP BGP 1.1.1.0/24, so it tells you that it is received from 45.10.11, which is basically R3, and is received from 35.10.11. which is R2, and it is considering this one as the best one. What is the AS path of this? It is 300, then 100. What is the AS path of this? It is 200, then 100. So here, according to BGP's path selection algorithm, the better way of reaching 1.1.1.0 is via R2. But for example, let's say I want to prefer the way which is via R3. So what I can do is I can create a prepend path. What I can do is I can add autonomous into the path. So if you remember when we were talking about BGP path selection criteria, the fourth point was shortest AS path. So for example, if in this scenario, if in this case, before 200, I add some more autonomous systems. Let's say I add autonomous system 100 two times again. So it will become 100, 100, 100, then 200. As a comparison to which this is simply 100 and 300. So BGP will understand that one is having 4 autonomous systems and one is having just 2. So according to that calculation, this one should be considered as the best path. So it will start going to R3 to reach 111.0. So this is a way how you can manipulate the BGP metric here. So let's see how this can be achieved. I'll go to R1. Here, first of all, I have to define the traffic which I'm willing to manipulate. So I'll create a IP prefix list, config T. I'll say IP prefix list, and I can simply give it some name. Let's say PyNet. Then I'm going to say permit. What network? 1.1.0/24. After that, I'll create a route map for adding autonomous systems into this particular 111.0's advertisement. So I'll say route-map. You have to give it some name. So let's name it as metric modifier. Enter. Then I'll say match IP address from the prefix list which we have created with the name PyNet, like this. After matching the IP from there, I am telling it to set local. Okay, I'll set the AS path. So after AS path, if I put a question mark, I get this feature of adding prepend. So prepend to the AS path. Prepend means add something before the original value. So I'll say I want to prepend it with some value. Question mark, it is asking me what AS numbers you want to prepend before the original value. So I'll say I want to add, for example, 100 and then 100 again. So I want to add 100 twice in that. And then I can take the exit from route map. Now all I need to do is I need to apply this route map for my neighbor R3. Not R3, I think. Which one is the best one? Okay, it is currently considering R2 as the best one. So what I'll do is I'll make the path via R2 as the longer way to reach destination. So I'll apply my route map towards R2 so that as a comparison to R3's path, R3 comes out to be the better one, and R4 starts sending data to R3 to reach 1.1.1.0. That's what I will try to achieve. So I'll go back to my R1. I'll go into my BGP configurations, router BGP 100. I'll call my neighbor R2 there, 23.10.1.2. And I'll say I want to apply a route map on this with the name metric hyphen modifier for my outbound routes. Enter. After this, I'll go back to my R4. Let's see what's the difference now there. I'll check the same command again. Okay, as of now, the things are not updated. I'll check it again. So BGP being a slow protocol might take a little time. Okay, there you go. Now observe this. Earlier, when we were checking this information, the path via 35.10.11 had the AS path of 200 and 100, right? But now, since we have applied a route map there to prepend the information, we will see that the AS path got changed from 200, 100 to this. Why is this? Because we added twice 100 autonomous systems to prepend into the information. Make sense? So we made it a longer way intentionally. And now I can see the best way of reaching the destination is via 45.10.11, which means R3. So this is the best way now, right? If I check my routing table again, if I say show IP route, so I can see 1.1.1.1, 1.11110 is reachable via 45.10.11. Make sense, guys? That's how basically you can manipulate the metric here in BGP also. Just like I have changed the AS path, you can do manipulations using various other values also, which we have discussed in all those factors. So depending upon how you wish to manipulate it, you can change the local preference, you can change the multi-exit discriminator value as well. Various things can be done with BGP. And depending upon your scenario, you can take up the appropriate factor which you want to manipulate and can change the value there to make sure that your BGP router selects your selected one path only to reach the destination. So if you have got any questions in this, then please let me know. All right. So understanding the impact of metric manipulation, as I mentioned in the beginning also, is very, very, very crucial and important before getting started with metric manipulation. Now, some of the, we can say, benefits of using it can be improved network performance, right? Probably, let's say R3 is the stronger router as compared to R2. That's why I want to send the traffic via R3. So I can make sure that it selects R3 only, not R2. This is a better way, right? This is a way how I can improve my network performance. But if, for example, we are doing it and we are not understanding the impact of it, it can lead to some suboptimal routing decision. It can select the, we can say, the route which might lead us to network congestion, right? It can create network loops. It can create more complexities. So to ensure metric manipulation is having a positive impact on your network, you can do various kind of things. Like, for example, before implying it on a real production scenario, you can try it on a simple EVNG lab, right? You can try it on a EVNG lab. You can understand the impact there. If you think this will help you in the real scenario, in the real life or real world example, then only apply it there. Make sense, guys? That's a possible way in which you can make sure that there is no network loops, or instead of increasing complexities, you are increasing the performance. So this is a way how you can make sure that metric manipulation is only helping you in a positive way and is not creating any negative impact in your network. So if you have got any questions regarding metric manipulations, then please let me know. Otherwise, that would be all from my side, and we are good to wrap up. All right, then. Thank you so much, guys. I hope you enjoyed the content of this webinar. This webinar was about metric manipulation. Now I leave it up to you guys how you want to explore this. And as you all know, we have a YouTube channel. This recording of webinar will be very soon uploaded on YouTube as well. So even in future, in case you get any queries or doubts, you can put that there in the comment box. Or otherwise, you can also join our Telegram group, which again will be mentioned in the description of that particular video. So you can join that channel. You can put up your questions there. You can ask your doubts there, and we'll be there to help you out as soon as possible. Thank you so much. That was all from my side. Signing off, Chirag Dhall, and thank you so much for your wishes. Thanks. I am really glad that you enjoyed the session. I'll see you in my next webinar. Till then, take care. Bye-bye. And keep yourself updated with these webinar informations by joining the Telegram group. So thank you. Bye-bye. Take care.